Hey, in this video, we're going to look at polynomial functions and how to get a rough sketch of their graphs. And this is going to come down to emphasizing x-intercepts and the behavior of the function on the ends and in the middle. We're not going to be terribly precise with our graph. That's why we're going to be sketching, just to get the rough idea. You can always make a graph more precise by plugging in particular x values and finding particular y values. But this is more for speed to understand the behavior of a polynomial function. Let's do our first example. Let's sketch the graph using end behavior and a sign chart. And I'm going to do this a couple different ways. The first way I'm going to do it is show you how to use your calculator to generate the sign chart. And then I'll show you some shortcuts for generating the sign chart. And then you can do with it what you want. So our first function is f of x equals negative 6x squared times x minus 3 times x plus 4 to the third times x minus 1. And one thing I really like about this function is that it's already factored for us. This is a polynomial function, meaning if you multiply it all out, you're just going to get a sum of powers of x. Okay? Now, let me mention something about a polynomial function first of all. A polynomial function is a smooth function, meaning no sharp corners. And it's a continuous function, meaning there's no breaks or no gaps, okay, no holes. So make sure when you graph these that you have smooth, continuous graphs. All right, so here we go. The way you want to start is by finding the x-intercepts or the zeros. So the x values that make this whole function 0 are the x values that make each factor 0. For example, if x is 3 and you plugged in a 3 for all the x's, you would see that, well, 3 minus 3 would turn into 0, and then it wouldn't matter what the rest of this stuff is. When you multiply it, you get 0. So in this problem, we have four zeros. And so let's set up a sign chart here. And we're going to list all of the zeros on our x-axis, our x number line, and then map those to the corresponding y values. So we have 4 zeros here, 0, which has a multiplicity of 2, 3, which has a multiplicity of 1, negative 4 has a multiplicity of 3, and 1 has a multiplicity of 1. Okay, so let's go ahead and map those zeros out. I'll use the multiplicities later to show you what's going on with those. So the first one we encounter from left to right is negative 4, which is multiplicity 3. And then 0 is the next one, has multiplicity 2. And then 1 has multiplicity 1. And finally, 3 has multiplicity 1. And we know that the corresponding y values for those x values is 0. These all output, make the function turn into 0. That's why we chose this. And so because this function is smooth and continuous, in between each of those x values, the function has to be positive or negative. It can't be 0. Okay, so what we're going to do is use our calculator here to kind of see what happens. So I'm going to pick some x values between each of these. Now, when we want to know the end behavior, meaning what happens on the ends of the graph, we want to use really big x values. So over here, I might use negative 1,000 or negative 10,000 even. And over here, I might use positive 1,000 as a test point. And then for the middle behavior, meaning between all the zeros, use anything you like. So maybe between negative 4 and 0, we'll use negative 2. Between 0 and 1, we'll use 0.5. And between 1 and 3, let's use 2. Okay, so let's see what happens when we plug in negative 1,000 for x. So the first thing I want to do is tell my calculator to put negative 1,000 as the x variable. So I'm going to type negative 1,000, hit the store button, hit the x button, and hit enter. Most scientific calculators have some sort of store feature like this TI-36X Pro. But now you can see I've got negative 1,000 stored for x. Now what I need to do is type my function, negative 6x squared times the quantity x minus 3 times x plus 4 to the third power times x minus 1. And if I enter, it's going to give me the value of that expression when x is negative 1,000. And we can see here it says 5.95 E21. That means times 10 to the 21st power. This is a huge positive number. So that means that my function approaches positive infinity in this region of my number line chart. So we'll mark in this region where x is negative 1,000 or getting really big in the negative direction, the y approaches positive infinity. So that's our end behavior, our left end behavior. As x approaches negative infinity, y approaches positive infinity. Now let's run through, let's actually look at the right end behavior here. So now I need to put positive 1,000 in for x. So I'm not gonna hit clear or anything. I'm just gonna type 1,000, store x, enter. And I don't have to retype my function. I can just use the up arrow to go find what I typed before. Once it's highlighted, I can hit enter and it will retype it. Then if I hit enter again, it will calculate the new value of that function when x is positive 1,000. And now we can see we get negative 6 times 10 to the 21st. That's a really big negative number. So our right end behavior says that as x approaches positive infinity, y approaches negative infinity. So I'll put negative infinity on this portion of my number line chart. Now I'm going to go through and plug in all the middle x values to find the middle behavior of our function. And now these parts of our function are only going to be positive or negative. They're not going to go to infinity because the graph has to be smooth, continuous, and connected. Okay, so let's go ahead and plug in -2 for x on the calculator. All right, so -2, store x, enter. Go up to our function and hit enter to highlight and select it again. So it's retyped it. Hit enter one more time, and in this case we get negative 2,880. That means our function is negative in that region. So when x was -2, we got a negative number. If you wanted to keep track of the exact value, you could do that and plot it on your final graph. But again, we're just sketching, not being precise. Let's go on to 0.5. Okay, if we plug in 0.5 for x, I'll do 0.5 store x. Now it's stored after I hit enter. Go select our function, hit enter, enter one more time to calculate the output. And in this case, we get negative 170.8 about. So when x is 0.5, we got a negative y value again. Finally, let's plug in 2. Okay, so 2, store x, enter, go reselect our function and calculate the output, which is 5,184. So when x is 2, we get a positive output. And now we have a complete number line chart, okay? We'll talk about how to graph this momentarily, but let me talk about the shortcuts for doing this. You don't have to use a calculator to do any of these signs. However, it's a dependable way to do it, especially when you don't have to keep retyping the function. You could just type it once and reselect it. It allows you to calculate outputs of these complex looking functions really quickly. So you might like to use that as a tool. But another way is to use end behavior by the leading term. If we were to multiply all of this out, the leading term would be -6 x squared times x, so that's -6x cubed, times another x cubed, so that's -6x to the 6th, times x is -6x to the 7th. And this leading term, -6x to the 7th, approaches positive infinity on the left and negative infinity on the right. So that gives you your end behaviors right away. But what about your middle behaviors? Well, this is really interesting. The multiplicities can help you with that. When you have an odd multiplicity like 3 or 1, what happens is the signs on each side, the outputs on each side, should have opposite signs. So since this is an odd multiplicity, and we had a positive sign, positive output on the left, that means we have to have a negative output on the other side. And you can see here, multiplicity 1, the signs of the outputs are opposites on each side of that. And finally, at 3, we had a multiplicity of 1, and the signs of the outputs are opposite again. Now, if you have an even multiplicity, like 0 has a multiplicity of 2, then the signs on each side are the same. In this case, they're both negative. So you can see if you just use multiplicities and you get your end behavior using the leading term first, then you know this is positive infinity with an odd multiplicity here, so that's going to turn into a negative sign for the next region. Then you have an even multiplicity, so the sign stays the same. Then you have an odd, so the sign changes. Then you have an odd, and the sign changes. So you can also generate your signs very quickly with end behavior from the leading term and multiplicities. So choose whatever you like there. But now that we've got a complete sign chart, let's go ahead and sketch the function. So let me mark my zeros, -4, 0, 1, and 3. And I know y is 0. That means our function is on the x-axis. Then my left end behavior goes to positive infinity. Between -4 and 0, my y value is negative. That means below the x-axis. Then from 0 to 1, I'm negative again, below the x-axis. And then from 1 to 3, I'm positive, meaning above the x-axis. And then after 3, I have to approach negative infinity. And so that's it. That's how easy it is to sketch the graph. Now, if you wanted to know precise y values, then you could keep track in your calculator of what those y values are, and you could plot more points. But we are just sketching using basic end behavior and middle behavior. Now, in the rest of the examples, I'm not going to do all of the calculator work. That's easy to do, but I'm going to generate the sign chart quickly and then show you the graphs. All right, so our second example, we're going to sketch the graph again. This time our function is f of x equals -x cubed minus 2x squared. And so the disadvantage with this example is that the function isn't factored. We need to factor it so we can find its zeros. So to factor this, we're just going to pull out a greatest common factor of -x squared, which is going to leave behind a positive x plus 2. Oh, that was pretty easy. It's factored now because x plus 2 doesn't break down further. The zeros, there's only 2 of them in this case, are 0 and -2. -2 comes first and has a multiplicity of 1, and 0 comes next, has a multiplicity of 2. And you can use your calculator or the leading term of -x cubed to see your end behavior. As x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to negative infinity. So we can put those up here for our y values. Oh yes, and at our zeros, our output, or our y values are 0 in this case. And then we could plug in -1 on the calculator, or we could use a multiplicity. This is an odd multiplicity, so I know this positive output is going to turn to a negative output here. All right, we have a complete sign chart. Let's sketch the graph. -2 is a 0. 0 is a 0. The left end goes to positive infinity. Between -2 and 0, we are negative y values, so we're below the x-axis. And then after 0, we go to negative infinity. And that is it. That's all there is to it. Just have to be able to factor. Okay, let's do one last example. We're sketching the graph of a polynomial function. Let's say this last function is g of x equals 6x to the third power minus 8x squared minus 54x plus 72. Again, not factored, so let's work through that first. So the first thing we're going to do is look for something common to everything, which I see a 2 goes in, leaving behind 3x cubed minus 4x squared minus 27x plus 36. And I got 4 terms, so I'll try grouping. My first group, I can pull an x squared out, leaving behind 3x minus 4. And my last group, I can pull out a negative 9, leaving behind positive 3x minus 4. Okay, that's good, because the 3x minus 4's match in our two groups. Let's pull that out, leaving behind x squared minus 9. Which factors more? So I get 2 times 3x minus 4 times x plus 3 times x minus 3. All right, fantastic. We're all factored. Now we need the zeros for our sign chart. And so we get 3 zeros out of this. Positive 4/3, right? If you set 3x minus 4 equal to 0, you add 4 and divide by 3, we can see that 4/3 is 0, and then negative 3 and positive 3. So negative 3 is first with multiplicity 1, and then 4/3 is a little bigger than 1, so that's next. Also multiplicity 1, and then positive 3 is next, also with multiplicity 1. And all of those output 0. Now we can use a calculator to see the end behavior, but I'm going to go ahead and use the leading term, which is 6x cubed. And we know 6x cubed, well, as x goes to negative infinity, y is also going to go to negative infinity. And as x approaches positive infinity, y is also going to go to positive infinity. So I'm going to go ahead and put in my end behaviors here. And then I can use my calculator to get the middle behavior, but I'm going to go ahead and use multiplicities, which are all odd. So this negative sign is going to change to a positive across this odd multiplicity. This positive changes to a negative across this odd multiplicity. And this negative changes to a positive across this odd multiplicity. And we have a complete sign chart. Let's look at the graph now. Let's see, negative 3 is a 0. 4/3 is a 0. And 3 is a 0. So those are all x-intercepts. Then we go negative infinity. Then we go above the x-axis, below the x-axis, and then to positive infinity. And that is it for graphing polynomial functions. You need to be able to factor, and at minimum, use your calculator to get the end behavior and the middle behavior, but you can also use the leading term and the multiplicities to do all that. So go get some practice. I think you'll like this. These are kind of fun to graph.